Week number 9, we talked about function notation. If I give you a problem like this, it says evaluate if possible. F of 1. So if f of x is equal to 2x minus 3, let me get my marker working here. Then I want to know what f of 1 is. Well, f of 1 is equal to, and then I just put 1 in for x. So 2 times 1 is 2 minus 3, so f of 1 is going to equal negative 1. If I want to know what f of negative 3 is, I do the same thing. I put negative 3 in for x, so this would be 2 times negative 3 minus 3. So this would be negative 6 minus 3, so f of negative 3 should equal negative 9. Now, if I want to find f of x minus 1, that's a little bit different. I do the same thing. I plug x minus 1 in for x, so this is going to be 2 x minus 1 minus 3. And I would multiply this through. That would give me 2x minus 2 minus 3, or 2x minus 5. So f of x minus 1 would equal 2x minus 5. Now, if I do the second one, and I want to find g of 2, I would just put 2 in there. So the g of 2 would equal f times 2 squared minus 3 times 2 plus 5. So this would be 4 times, that would be 16 minus 6 plus 5. So that would be 15. Now, if I was going to do t minus 2, again, I would have to plug this in. So this would be 4, and then t minus 2 squared minus 3, t minus 2 plus 5. Function notation, you're just plugging that in wherever you see the variable. That's it. And then we'd have to simplify it down and do the work on it. We also talked last week about finding domain and range. We talked about, or we just talked about domain, sorry, not range. To find the domain of a polynomial, it is always all real numbers. Now, if I want to find one of a rational function, remember it's all real numbers except whatever makes the denominator equal to 0. So all real numbers except x does not equal, and in this problem, negative 5. If I had a radical, remember, we just set whatever's inside the radical greater than or equal to 0 and solve. So if I add 10 to both sides, y is greater than or equal to 10. So this would be my domain. Any number greater than or equal to 10 would work in this problem. So finding the domain of polynomials, rationals, and radicals are fairly easy to do. This week, we're going to be talking about analyzing graphs of functions. There's a lot of stuff to get through this week, but a lot of it, there's not a whole lot of real difficult material in here. We're going to be talking about graphs of functions. We have studied functions from an algebraic point of view. In this section, you'll study functions from a graphical perspective. The graph of a function f is a collection of ordered pairs x, f of x, such that x is in the domain of f. So it's basically plotting points. As you study this section, remember that x is the directed distance from the y-axis. So let's say this point here is, let's see, it looks like 1 point something, 1.2, and this value is 2 here. So my x value is how far away from the y-axis I go, and the y point is how far up you go. So how far over, how far up, that's how you find the point. And you can, if you're going to graph something, you can just plot a bunch of points to get the graph. Use the graph of the function f shown in figure 2.13 to find the domain of f. Remember, the domain is how far over on the x-axis you go and how far over on the x-axis you go here. So my domain here looks like it would be -1 to 5. Yep, and that's an open dot, so okay. Now I could write it, I could go -1 is less than or equal to x, which is less than 5. That would work. Find the function values f of -1. Well, they're telling me that this is my x value. So -1, my y value is 1. So f of -1 is equal to 1. What is f of 2? Well, where's 2 here? 2, -3. So f of 2 is equal to -3. The range of f, means how far on the y-axis. So it looks like -3 is the lowest, +3 is the highest. So it looks like I would go between 3 and -3. Oh, I did that wrong. I should go from -3 to 3. We should always put these in order of which way they are written. Okay. By the definition of a function, at most one y value corresponds to the given x value. This means that the graph of a function cannot have two or more different points with the same x coordinate, and no 2 points on the graph of a function can be vertically above or below each other. Okay, so we talked about this in week 9 about the vertical line test, that if you draw a vertical line, for example, if I gave you a graph and I said, is this a function? Well, if you draw a line straight down, this touches in 2 places. This is not a function. The vertical line test tells us if something is a function or not. So if you draw a vertical line and it touches 2 on the graph, it's not a function. Okay, so the vertical line is a really easy way to tell if something is a function or not. Zeros of functions. Now, another way of saying the zero of a function is, what are the solutions? That, when students see find the zeros of a function, they don't realize that the same question would be find the solutions of the function. For example, if I gave you x squared plus 7x plus 12, and I said, I want you to find the zeros of this function. Well, that's the same thing as saying, hey, what are the solutions? So if that's set equal to 0, if I factor this, x plus 5, x plus 2, no, that does not work. 4 and 3. So -4, -3. So those are my zeros of the function. Now, if we graph this thing, we know that at -4 and -3, this parabola is going to cross. Those are the zeros of the function. Why do they call them zeros? Because if you look at this, this would be -3, 0, and -4, 0. The y value is 0. That is why they call them the zeros of the function. Okay, it's the x value when the y is equal to 0. So if the graph of a function of x has an x-intercept at a0, then a is the zero of the function, or it's a solution. Zeros of a function of f of x are the x values of which f of x equals 0. So it's when you solve an equation set equal to 0. Find the zeros of the function. Now, we've been finding values or solving polynomial functions, radical functions, and all that throughout the first 9 weeks of this class. So if I wanted to find a solution of any one of these, all I have to do, just set it equal to 0. So 10 minus x squared is equal to 0. If I wanted to solve this, I'd square both sides. So 10 minus x squared is equal to 0. I'd bring the x squared over, so 10 is equal to x squared, take the square root. So I'd end up with plus or minus the square root of 10. We've been solving polynomial, radical, and rational functions this whole time. So if they'd ask you to find the zeros, that's all it's asking you to do. It's just asking you to set it equal to 0 and solve. If I did the polynomial one, I've got 3x squared plus x minus 10 is equal to 0. Now, I'm not sure this is going to factor, but if I did factor it, I would use the cheater method. So I'd put 3x here, 3x here, multiply this out. So that gives me -30. Is there 2 numbers that multiply to -30 that add up to 1? Yeah, -6, +5. So it does factor, but guess what? I still have to divide a 3 out of one of the parentheses because I cheated with a 3. So x minus 2, 3x plus 5. So my solutions to this problem would be x equals 2 or x equals -5/3. So if they'd ever ask you to find the solutions or the zeros, you could always solve like we've been doing, or you could graph the function out. If I graphed this function right here, I guarantee you that it's going to cross at +2 and at -5/3. I know it has to. Why do I know it has to? because those are the solutions. So if you graph it out, you're going to find the zeros also. So either way works in these types of problems. So a practice problem for this week, it says find the zeros of the function algebraically. Okay, so if it says algebraically, they want you to work it out. They want you to graph it. So I've got 2x squared minus 3x minus 20. I can't factor anything out, so I'm going to use the cheater method again. So I'm going to go 2x, 2x. I'm going to have to divide a 2 out at the very end. If I multiply across here, I get negative 40. What two numbers multiply to give you negative 40 but add up to negative 3? How about negative 8 and 5? So minus 8, positive 5. I've got to divide a 2 out. So x minus 4, 2x plus 5. So my solutions are negative 5 halves and 4. Looks like letter A for that one. So finding the zeros is the same thing as solving the function. Exactly the same thing. Increasing and decreasing functions. If we're looking for if a function is increasing and decreasing, all we have to do is graph it out, and then we read from left to right. So this is my left-hand side. Looks like my function is decreasing, then it's constant, then it's increasing. So just by looking at a function that's graphed out, we can tell where it's increasing, decreasing, and constant. Now, when you get to higher up math like calculus, we spend a lot of time trying to figure out where functions are increasing, decreasing without looking at their graphs. And that is pretty cool stuff, taking derivatives and all that. Increasing and decreasing function, it just basically what it is, if you read from left to right, it's increasing if it's going up, it's decreasing if it's going down, it's constant if it is horizontal. Use the graphs to describe the increasing, decreasing, or constant behavior of each function. Okay, so this function, x to the third, it's always increasing. It's never decreasing. Looks like it could be constant right here, but I don't think so. I think it's just an inflection point right there because I know my calculus. So it's always increasing. This problem, it's increasing from negative infinity. We just assume that it keeps going to negative 1, so it's increasing. Then from negative 1 to positive 1, negative 1 to positive 1, it's decreasing. And from 1 to infinity, it is increasing. Now, I'm using my x values. I'm not using my y values. Your values tell you where it's increasing and decreasing. In this problem, it's increasing, negative infinity to 0, 0 to 2, it's constant, 2 to infinity, it is decreasing. The points at which a function changes its increasing to decreasing or constant behavior are called relative mins and relative maxes. The definition of a relative min and a relative max, the function value f of a is called relative minimum of f when there exists an interval that contains a such that, and then it basically is saying it changes directions. Okay, you know, if I have a function like this, got a max here, a min here. Now, they're talking about relative maxes and relative mins. You can have absolute maxes and absolute mins also. Like if I had a parabola that looks like this, and I knew that it was never going to come back, you know, that this function was never going to turn around and come back up, this would be considered an absolute max. Now, our book considers it a relative max also, but it's the highest point around the area. Okay, so there's no other point that's higher around the area. Now, if this graph came back up and went like this, this would also be another maximum value. Okay, so we're talking about relative max and mins. Max is the highest point on a graph. Min would be the lowest point on a graph. So if I had a problem like this, it shows that this is a relative min, relative max, relative max, because we don't know what's going to happen at the, if this function kept going up and up and up, obviously this point here is higher. We don't know what the end of the graph is going to do, so we just call them relative mins and maxes there. We will study a technique for finding the exact point at which a second-degree polynomial function has a relative min or relative max. For the time being, however, you can use a graphing utility, so use Desmos to figure out max and mins. In this problem, it says determine the intervals for which the function is increasing, decreasing, or constant. Okay, so increasing, now I don't know if it continues going down forever. It sure looks like it because, you know, that's usually how it works. So it's increasing from negative infinity to 0, so it's increasing. Then it's decreasing from 0 to 1, so that's decreasing. Then it looks like it's increasing from 1 to infinity. So just looking at a function, you should be able to tell if it's increasing or decreasing just by looking at its graph. Now, the last thing that we have to talk about today is average rate of change. We know what slope is, okay? To find the average rate of change between 2 points, all we have to do is find the slope between those 2 points. So, for example, if I wanted to know the average rate of change between this point and this point, all I do is I just draw a secant line in, and then I find the slope between those 2 points. So if they give you a function and they want to know what the average rate of change is between those 2 points, you just find the endpoints, find the slope between those endpoints. So for example, if I gave you a problem, secant lines, the formula for slope is y2 minus y1 over x2 minus x1, which is basically this. So if I gave you a problem like this, it says find the average rate of change for the function x to the third minus 3x, that's this graph, from -2 to -1. So -2 is right here. So that point, I can see it right on the graph, is -2, -2. And the other point is -1, 2. And here is the secant line. Looks like that. It looks like, you know, if I did it correctly, it looks like the secant line is positive. So it definitely is going to have a positive slope there. So if I do my slope formula, so that's going to be 2 minus -2 over -1 minus -2. So that's going to be 4 over 1. So the slope here, or the average rate of change between x1 and x2, is going to be 4. So to find the average rate of change, all we're doing is we're just trying to find the slope between the given points. So in this problem here, it says find the average rate of change of the function from 0 to 3. Well, I was going to say, I don't know what this function looks like, but I sure do. -4, that's a graph that looks like this, doesn't it? Now, I don't even have to do any work because the average rate of change is the slope. Well, this is a linear function. The slope has to always be -4. It's not going to change. I don't care which points you pick. That slope is going to be the same. So I'm going to say the average rate of change between 0 and 3 has to be -4. I mean, it can't be anything else. So the average rate of change has to be -4. It has to be. And it doesn't matter what points you pick on that graph. It's going to be the same. In the near future, we're going to be graphing, and we're going to be doing a lot of transformations of graphs. So what we need to know is we need to know the parent graphs. So this is a constant graph. There's always a horizontal line. If we have f of x equals x, this is what we call the identity function. Absolute value, this is the parent function. Square root function. We also have the quadratic function. This is the parent function. And what it means by parent function is it is the very simplest form for that graph. So for example, there's a lot of parabola graphs, right? You could have y is equal to x squared plus 4x plus 5, and that graph would, you know, be over here someplace. But the parent function is the very simplest form, x squared. That is the parent function for a quadratic. For a cubic, there's so many different cubics, but the parent function is this. Now, why is this important? Because in the near future, we're going to be shifting these graphs. For example, I might give you this function, x plus 2 squared minus 3. It's like, oh, how does that shift this parent function? Well, I know it's going to shift it 2 places to the right. Nope, it's going to shift 2 places to the left and 3 places down. So 2 places to the left, 3 places down. So this function is going to look exactly like the parent function, but it's going to be shifted. That is called a transformation. We're going to be spending a lot of time with transformations in the near future. But these are the parent functions. And there's really nothing on the assessment about this. I just wanted you to see the parent functions for each one of these graphs, because when I start talking about parent functions, and I'll say, what is a parent function for x squared? You should know what that is.